Hi guys. Well, in the last lecture we have already discussed the entire strategy to compute the optimal feasible solution for an LPP provided it is existing, right? Well, depending upon the feasible region being bounded, unbounded, there are different steps which we understood in the algorithm of corner point method which we need to follow in order to get to the optimal feasible solution. Let's begin the application of that algorithm and practically see how do we need to work and adopt the steps in the algorithm to get our very solutions. Here we have this LPP. This is my linear programming problem. In this linear programming problem, I am being asked to maximize the objective function z. So, z is given to be a linear function in two variables. That's my objective function. This is my objective function, linear function in two variables. I am being asked to find the maximum value of z. You will always be asked to optimize the objective function. That optimization can be either maximization or minimization. Here you are being asked to maximize. Subject to these constraints are there. So, these are the constraints which you have to keep in mind when you are moving ahead to maximize z. Also keeping in mind these two more constraints known as the non-negativity restrictions. So, when I am being asked to solve this LPP graphically, that means I am being asked to find that value of x and that value of y, which when I will be plugging in over here, I will get maximum value of z provided that x and that y satisfies all these three constraints and is a non-negative value. Okay? So, I want such an x, such a y which satisfies everything written over here, and when you plug it in here, you get the maximum value of z. Okay? Obviously, we will be adopting the corner point method to solve it. What does it say? The corner point method in the very first step says that obtain the feasible region of the LPP and identify the corner points by inspection or by solving the two equations of the lines whose intersection is that corner point whose coordinates are unknown. So, step number 1 will always be to obtain the feasible region. That feasible region is definitely going to be a convex region. It can be bounded or unbounded, that we have to identify and then accordingly proceed ahead. So, let's begin first of all the very computation of the feasible region of the given LPP. Okay? Now, how do you obtain the feasible region? You have the first constraint. Let's just see how many constraints do we need to plot. 1, 2, 3, 4 and 5. So, 5 equations we have to consider from these 5 inequations and then plot them. X plus 3y equal to 60 will be the first equation you will be considering. X plus 3y equal to 60. This is a straight line, fine. When x is 0, y is 20. When y is 0, x is 60. So, when x is 0, y is 20. When y is 0, x is 60. So, you will be getting a straight line somewhat like this. This point is 0, 20 and this point is 60, 0. And this is my straight line x plus 3y equal to 60. What is the region which is represented by the inequation x plus 3y less than equal to 60? The region which is represented by x plus 3y less than equal to 60 will be either this side of the half plane or this side of the half plane, wherein this line is actually dividing this entire coordinate plane into two half planes. So, one of the half planes along with the points on the line is going to be the region represented by this inequation. How do we find that? Pick up a point which is lying on either side of the half plane from this line. This is one half plane, 0, 0 is a point lying in this half plane. So, plug 0 over here, you get 0 plus 0 is less than 60, which is true, and therefore, the region which consists of the origin is going to be the region which is going to be represented by x plus 3y less than equal to 60. So, everything on this side is my region. So points on the line and points on this side of the line, the half region which is on this side of the line will be the region represented by x plus 3y less than equal to 60. Fine. Moving towards finding the region represented by this inequation. X plus y greater than equal to 10. So you have x plus y equal to 10 first of all. When x is 0, y is 10. When y is 0, x is 10. So you would actually be getting, so this is 10, this is 10. So you would be getting somewhat like this straight line. I am not extending it. I don't need that extension. This is my straight line. This is x plus y equal to 10. This point is 10, 0 and this point is 0, 10. Again, if you only focus on this line, this is again dividing this entire coordinate plane into two half planes. Which half plane along with the points on the line is going to be the region represented by x plus y is greater than equal to 10. This is one point which is lying on one of the half planes in which this line is dividing the entire coordinate plane. So 0, 0 when you plug over here, you get 0 plus 0 is greater than 10. 0 is greater than 10, that is false. That means the region which consists of 0, 0 will not be the region which would be represented by x plus y greater than equal to 10. Rather the one which is on the opposite of it, that means the other region which does not contain the origin. That means everything on this side. Everything on this side of the line is going to be the region represented by x plus y greater than equal to 10. Fine. So points on the line and points on this side of the line is representing the region represented by the second inequation. Moving to the third, x is less than equal to y. Again, if you consider this equation, x is equal to y. X equals y is a straight line passing through the origin inclined at an angle of 45 degrees with the positive direction of x axis. So this is my x equal to y line. Okay. I am saying I want x is less than equal to y. This line is again dividing this entire coordinate plane into two half planes. Which half plane along with points on the line is going to be the region represented by x less than equal to y. Pick up a point which is lying on either of the half planes. Let me say on this side of the half plane, pick up a point, say 0, 10 you pick up. It is lying on this side of the half plane. So 0, 10 when you pick up, put x equals 0, y equals 10. 0 is less than 10, yes that is true, that means the half plane which consists of 0, 10 along with the points on this line is the region represented by x less than equal to y, which is everything on this side of the line. So line and this side of the half plane in which the line is dividing the entire coordinate plane. Is it understood? This is the region represented by x is less than equal to y, and after this I have x non-negative, y non-negative, that means everything restricted to the first quadrant. X greater than equal to 0 and y greater than equal to 0 is nothing but condition that everything is confined in the first quadrant. Because when I am saying x is non-negative, y is non-negative, that means the ordered pair x, y has both coordinates non-negative. That only happens when the point lies in the first quadrant. So now if all the points in the first quadrant are being representing the region represented by x greater than equal to 0 and y greater than equal to 0, and these are all the regions represented by all the other constraints, I am saying which are the points which are satisfying this also and this also and this also and this also and this also. They are those points which are lying in the region represented by this inequation also, this inequation also, this inequation, this inequation, this inequation. That means those points which are lying in the intersection of all these regions are the points which are satisfying all the 5 constraints. Fine. So I need to actually pick up the intersection. When you talk about the intersection, you will be able to see that this happens to be the intersection. Is it understood? This happens to be your intersection of the regions represented by all these 5 inequations. Is it clear? So this is your x equals y, this is your x plus 3y equals 60, and this is your x plus y equals 10. This happens to be the region which is common to all the regions. Clear? So along with the boundary, this is your region. and therefore this is my feasible region which is bounded and it has 4 corner points. Say this point is point A, this point is point B, this is C and this is D. If this shaded region is representing all such ordered pairs x comma y which are satisfying all my constraints including the non-negativity restrictions, that means this is the set of all feasible solutions. So this is my feasible region. This is my feasible region. A, B, C, D is the feasible region which is bounded convex region. Isn't it? It is convex. You can see you take any 2 points in this region, when you join them the entire line segment is going to lie inside this itself. So clearly it is convex, it is bounded. The convex regions which come up as feasible regions can either be bounded or unbounded. Right now in the problem I am getting bounded feasible region. So what am I going to do? The moment I have bounded convex region as my feasible region, I am super happy. Because I know that definitely my LPP is going to possess at least one optimal feasible solution. This is not that LPP which is going to possess no solution. Fine, definitely there will be at least one optimal feasible solution. Okay, and that will occur at one of the corner points. So, the moment I have bounded with me, what was the step 2 of corner point method? It said that identify all the corner points. Right now we don't have all the corner points identified. Let's do that. Let's identify all the corner points. Corner points, that's, let's say that is step 2. Corner points. Okay. Corner points is point A. Point A is 0, 10. That is already identified. Point B is something I don't know. So point B is actually the intersection of x equals y and x plus y equals 10. X equals y and x plus y equals 10. Put y in place of x, you get 2y equals 10, so y is 5. When y is 5, x is also equal to 5. So this point is nothing but 5, 5. B is nothing but 5, 5. So because by inspection it was not possible to get the coordinates of point B, which was my corner point, so I solved the equations of the two lines whose intersection is point B. After that I have point C again, whose coordinates directly to get by inspection is not possible. So I solve the two equations of the two lines whose intersection is point C. One is x equals y and one is x plus 3y equals 60. Put y in place of x, you get 4y equals 60, which means y is 15. And when y is 15, x is 15, so C is 15, 15. These are the coordinates of point B and point C. Okay? This is 15, 15. And point D's coordinates are already known to me, it is 0, 20. So I have all the corner points with me, and then the algorithm said to compute the value of the objective function at these corner points, because one thing is sure, because my feasible region is bounded, my LPP is definitely going to possess at least one optimal solution, and that will be at one of the corner points. Clear? That is why I have all the corner points, and also if one of the corner points, at least one of the corner points is definitely going to be my optimal feasible solution, that means corresponding to at least one of the corner points, the value of z that I am going to get will be my maximum value, because my problem is maximization problem. So what is that maximum value of z which is attained at least one of the corner points? Let's find out. Value of the objective function z, which is equal to, it's given to me as 3x plus 9y. So that is my z, z is 3x plus 9y. Fine, either you can write it like this or you can simply say value of z, which is equal to 3x plus 9y. Fine. That is already my objective function, that's known to me. So let's find out when x is 0, y is 10, what is my value of z. Here z is equal to x is 0, y is 10, so value is 90. X is 5, y is 5, what is z? X is 5, y is 5. 15 plus 45, that gives you 60. Then you have x is 15, y is 15. 3 into 15 plus 9 into 15, that is my z. This is going to give me 180. And then I have x is 0, y is 20. This is z, that is 3 into 0 plus 9 into 20, 180. So I have obtained the value of objective function at each of the corner points. Clear? I am being asked to get the maximum value of z. So in my algorithm I said that declare capital M to be the largest value of z that you are obtaining out of all the values of z at all the corner points, and declare small m to be the smallest value of z that you are obtaining. But right now we don't need small m because we are being asked to get the maximum value of z, so we only are required to talk about capital M. Clear? Capital M is what? 180. When the region is bounded, this is what? Largest value of objective function. If this is 180, that is the largest value of the objective function, this is the maximum value of z. That means maximum value of z is 180. But the question was to find the optimal feasible solution at which this maximum value of z is being obtained. Right now, if you talk about the data that we have, 180 is the maximum value of z which is being obtained at 2 corner points. There are 2 corner points which are happening to be my optimal feasible solutions, because at them I am getting the maximum value of z, that is 180. The moment I have 2 optimal feasible solutions, go to the diagram. Optimal feasible solutions are C and D. Whenever 2 corner points are able to give me optimal value of the objective function, then not just these 2 feasible solutions are my optimal feasible solution, but in fact in my algorithm I have written that when you join these 2 points, each point lying on the line segment joining these 2 points is also going to give you the same very value of z. You pick up any point in between C and D. Say this point is E, you pick up. Any point lying on the line segment joining C and D, you pick up. That point is going to have some x coordinate, some y coordinate. When you will be plugging it in here in the definition of z, you will be getting 180 only. You pick up any point lying on the line segment joining C and D. When you plug in the x and the y coordinate of that point in here, you will be getting 180 only. That means all the points lying on the line segment joining C and D, including C and D, are the points which are lying in my feasible region at which I am getting the maximum value of z. So right now I have infinitely many optimal feasible solutions. Many times students do this mistake, they commit this mistake that just because they see these 2 points delivering you with the maximum value of z, they say that this LPP has 2 optimal feasible solutions, one is 15, 15 and one is 0, 20, but that's wrong. That is utterly wrong. So capital M is 180, which is the largest or maximum value of z, as C and D are the points or are the corner points at which z is maximum. Therefore, all points lying on the line segment, all points lying on the line segment joining C and D, all points lying on the line segment joining C and D, including C and D, because at C and D you are already getting 180, that is the maximum value. In fact, every point which is going to lie on the line segment joining C and D is also going to give you 180 only as the value of Z. So, all points lying on the line segment joining C and D, including C and D, are the optimal feasible solutions of the given LPP, at which Z is maximum. Fine, and therefore this LPP has infinitely many optimal feasible solutions. Is it understood? This is that LPP which has infinitely many optimal feasible solutions. So just one word of caution, we have just adopted all the steps from the algorithm of corner point method. You only always have to use this in order to get to the very optimal feasible solutions of the given LPP. So the first step was to get the feasible region. Once we got the feasible region, we identified all the corner points. At all the corner points, we got the value of Z. Because my very feasible region was bounded, therefore, the largest value of Z was the maximum value of Z of my LPP. That was being obtained at whichever corner point, that was my optimal feasible solution. If only one corner point would have been there which is giving me the maximum value of Z, and only that point, only and only unique point would have been there which would be my optimal feasible solution. But the moment I have more than one, that is 2 corner points at which I am getting the maximum value of Z, in that case 2 points are not optimal feasible solutions, but in fact infinitely many are optimal feasible solutions, because the line segment joining those 2 corner points happens to give me infinitely many points which give me the exact same value of Z, and hence get qualified to also be optimal feasible solutions, which in turn in the end gives me that this LPP has infinitely many optimal feasible solutions, out of which Tues coordinates we know C and D is, C is 15, 15 and D is 0, 20. So x equals 15, y equals 15 is one such value of x and y which is satisfying all the constraints, and when you plug it in here and here, the value of Z is maximum, that is 180, and 0, x equals 0, y equals 20 is another value of x and y which is satisfying all my constraints, and when you plug it in over here and here, you get the maximum value of Z, that is again 180. Apart from them, there are also infinitely many points whose coordinates you don't need to know. The only conclusion is important, that there are infinitely many optimal feasible solutions of this LPP. What happens to be the case with other scenarios of LPP, we will be decoding in the next lecture, so I will see you then. Thank you.